Okay, the first topic here for nuclear power will be the neutron's role in creating a chain reaction. The first definition you should know is neutron activation, and that is where a parent nucleotide is bombarded with a slow or slow or thermal neutrons. Okay, so typically you'll have uranium, like 235 is a common one where you'll have, that'll be your parent nucleotide, and as neutrons move towards it, there's usually some device there to slow them down. They will stick in the nucleus, and that will cause an imbalance in the force between the protons that are repelling, and that will cause it to split into two parts, one larger, one smaller. So then you'll end up with two daughter nucleotides, as well as beta particles and gamma radiation. And then in this reaction, there are laws that go along with it. So momentum is always conserved. The total charge from the reactants to products is always conserved. The number of nucleons remains constant. And the really important one is that mass energy is conserved. So if the mass of the products in a reaction is less than the mass of the reactant, some energy will be created, and you can see that in the equation E equals mc squared. So here's an equation for a fission reaction that we talked about earlier. So the uranium-235 would be your parent nucleotide, and once it's bombarded with a neutron, it always splits, like I said, into two daughter nucleotides, and those aren't always specifically, there's never two specific products, but one will always be larger than the other, and then you'll result in a certain number of neutrons that are given off from this reaction. That are given off, and typically they'll range from 2 to 3 is a typical range, and that's 2 to 3 is what you want for an ideal ideally what you want to keep the chain reaction going at a sustainable amount. Because if you have too few neutrons that are after one reaction has occurred, the reaction might not continue on, because these neutrons would go and be part of the reactants for a different reaction. So if there's too few, you won't get that sustaining chain reaction. But if there are too many, the chain reaction will go too quickly, which can cause a nuclear meltdown or an explosion. That's when you have, that's what you'll see in a nuclear bomb or something of that sort. But in nuclear production, where it's more controlled, you'll see 2 to 3 neutrons every time you emit it to just control the speed of that chain reaction.
Okay, so fuel enrichment is a process by which uranium-235 is increased in fuel, which is usually uranium-238. But by increasing the uranium-235, it increases the fission, which is the chance of the reaction to occur and for nuclear reactions to take place. So usually they increase it from about 0.07 to 4%, and that's just a pretty big concept because that's how the nuclear reactions and the nuclear fissions do occur, by having more uranium-235 in it. And then the other point that I had was energy transformations in a nuclear power plant. It's kind of a process, but it starts out with the core, which is a nuclear reactor, and then it produces nuclear energy, which goes into it creates steam, because you cool water down with it, and then that makes the steam, and it's the coolant process by producing steam, which makes thermal energy. Then you harvest the steam, so to speak, through a wind turbine, not a wind turbine, but a steam turbine, sorry. And then this steam turbine, it has a lot of thermal energy lost as heat, to the environment and to the places around it. And then that kinetic energy goes into generators that's left over, and then the generators go to distributors, and that's when it turns the kinetic energy from the turbine into potential kinetic energy for people and consumers to use, which is electrical energy, as we call it. And then it's roughly 30% efficient. It varies from 30 to 46 at the max, but other than that, they're pretty inefficient.
Alright, so I will be explaining what the role of the moderator is and also the control rods within the nuclear power system. The moderator is pretty much only used to slow down the fast neutrons to the necessary speed for the reaction, because there's slow neutrons already present and then there's the fast ones. and the fast ones need to be brought down to the same speed as the slow neutrons. And another thing about the moderator is it must have a mass that's extremely close to the mass of the neutron, otherwise the reaction will not occur. So some examples of what type of material the moderator can be made of is water, heavy water, graphite, beryllium, and liquid sodium. And also another key component of the nuclear power system is the control rods, which their sole purpose is to control the rate of fission within the reaction. And then a constant you'll just need to know is that the energy in one fission is 200 mega electrovolts. And then radiation shields are also necessary in a nuclear power plant so that the workers will not get radiation poisoning. So the radiation shields are made up of concrete, and there's 2 shields to ensure that no workers will be harmed when performing the reactions. Alright, the role of the heat exchanger is really important within the nuclear power system. And first of all, you need to know what a heat engine is, and it is something that extracts useful work from the internal energy of a system. And then the heat exchanger it acts as a heat engine, so it gets work from the internal energy. And the heat exchanger is driven by the chemical reactions by the nuclear reactions.
Alright, so in this section we're going to be discussing the use of uranium and plutonium as nuclear fuel. Uranium has an isotope, uranium-238, which is a pretty common isotope. It's a stable isotope though. And if you have uranium-238 and you bombard it with neutrons, you chuck a bunch of neutrons at it, it'll capture a neutron. It's called neutron capture. And it gets a neutron, it becomes uranium-239, which is an unstable isotope. Because it's unstable, it decays. It goes through beta decay and decays to neptunium, which is also unstable, and that decays and forms plutonium, which is an element that is not found in nature and is only able to be man-made. Now, plutonium-239 is very important because it's a useful fuel that can be used in a variety of other reactors and weapons. If you add a neutron to plutonium-239 through this same neutron capture dealio, it will break up into barium and strontium and release a whole lot of energy. So plutonium-239 plus neutron yields energy and barium and strontium. And so how this is done is they have control rods made of plutonium-239 and uranium-235, which is another isotope of uranium. So control rods are made of plutonium-239, and uranium-235, which are placed in the reactor with a blanket, so that around these are uranium-238. This is like around the whole thing. And that helps increase the efficiency of the reaction. And this fission is the word for breaking apart, which is what all of these reactions are. The other term would be fusion, which means putting them together. And you can't do that yet. We haven't gotten advanced enough to successfully do fusion. But fission, breaking apart, produces on average 2.4 neutrons when you break apart plutonium. So you produce 2.4 neutrons. You have to use 1 neutron to make the reaction go again. And so you yield a net result of 1.4 neutrons. So it is 140% efficient in terms of making power and energy. And so, for example, if you have 100, that's not going to be able to see that. If you have 100 uranium-235s, and they go through this whole process of fission, they're going to produce 240 neutrons. Now you you're going to need 100 of those for your reactor to go again, because you want to make 100 more of these uranium-235s. So you're going to end up with 140 neutrons left, which is where you get your 140% efficiency.
So when utilizing nuclear power, there are plenty of risks involved, but there are also benefits, like it reduces pollution because it's far more efficient than fossil fuel, and also the reserves that we currently have can last up to 2,000 years with the current rate of use, but if we do a large switch to nuclear power, then they could end up lasting only 100 years. And the major risks with going to nuclear power, first of all, are that it's difficult to mine the uranium and it's also dangerous for the workers. And the nuclear waste is dangerous and thus needs to be disposed of, but it's also difficult to find a place to put it where it won't hurt people. There's a risk of the reactor melting down, and there's also a possibility that some nations might utilize the reactors to produce weapons. Another way to get uranium is that you can take it from seawater. However, that is a lot less beneficial than mining it because you get far less uranium based on the time and resources invested. The half-life of most nuclear material is about 30 years. However, plutonium has a half-life of 24,600 years, which is a very long time to store the material. So disposing of it is difficult, but the ways they currently have of doing it, first of all, is to bury it in bunkers deep underground where the radiation will not affect groundwater or people living around it. And the secondary way of doing it is to grind the waste into a powder and forming it into a synthetic rock. Okay, 8.4.10, problems with nuclear fusion. Nuclear fusion is a very clean source of energy and it produces very few radioactive waste forms. However, it does require much more energy to maintain it than we can currently extract from it, so hence it's not really a source of energy at all because it utilizes power instead of giving it to us. To make it work, we need seawater and lithium. Deuterium is extracted from the seawater while lithium is made into tritium. These things are then fused, thus causing a neutron to be released. It collides with other particles to create heat, which is then used to heat up hydrogen isotopes. Those then form into a positively charged plasma that expands in all directions. The plasma must be confined for at least 1 second with a density of 500 trillion atoms per cubic centimeter, and these conditions must be maintained for the reaction to be beneficial because it is not a chain reaction, hence it cannot maintain itself.